time to start, Ruth? Okay. Hello, everyone. My name is Alia Hami. I'm an associate professor in math at UMBC, and I will be hosting this session. First, I would like to start by acknowledging that I'm joining you today from Prince George, Northern BC, situated on the traditional unceded territories of the Lheidli First Nations. I am I feel fortunate, and I'm very grateful to be able to live and work on this land. So welcome, everyone, and thank you for joining this PIMS network-wide colloquium. And it is my immense pleasure to introduce our speaker for today, Dr. Kristen Lauder. Dr. Lauder is an American mathematician and cryptographer. Her research areas are broadly in applications of number theory and algebraic geometry in cryptography. She is particularly known for her work in elliptic curve cryptography. From 1999 until 2021, she worked as a researcher at Microsoft Research in Redmond, Washington. And in 2008, she became the head of cryptography research group at Microsoft. In 2021, she joined Facebook AI Research as the West Coast head of research office. She's the recipient of many recognitions and awards for her vast and immense contributions to mathematical research and the mathematical community. And among these awards, just to mention a few, she's a fellow of the American Mathematical Society, a fellow of the Association for Women in Math, and the Society for Industrial and Applied Mathematics. She served as the president of the Association for Women in Mathematics from 2015 to 2017. And I would especially, as a number theorist myself, I would especially like to highlight her immense contributions to the number theory community, particularly through the network, the Women in Numbers Network, which she has co-founded. And this network has not only inspired female mathematicians in number theory, but it's also inspired similar models for research collaboration networks for women in other areas of mathematics. So thank you, Dr. Lauder, for being here with us today, and the floor is all yours.
Thank you so much for that very kind introduction. So let me pull up my slides. And while I'm doing that, I'd like to acknowledge that WIN was actually founded jointly with Renata Scheidler, who's on the call. Always a pleasure to see you, Renata. Thank you for inviting me. And Kate Stang. And WIN has been a really great part of my career. So today I'd like to talk to you about my new research over the last couple of years. So let me see, I'm trying to let's play this from the start. Are you able to see the slides well? Yep. Great. So I'm going to talk to you about our series of papers, the SALSA paper. I'll tell you what SALSA means later, and the PICANTE variant of it and the SALSA VERDE variant of it. And PICANTE and VERDE are both being presented. They're both accepted for conferences next month. PICANTE will be at CCS, which is a top security conference, and VERDE will be at NeurIPS 2023, which is a top machine learning conference. So the topic that I'm going to talk to you about today is actually using AI or machine learning to try to understand the security of and mount new attacks on post-quantum crypto systems, in particular lattice crypto. So that's why, like, the short title for my talk here was just AI for crypto. And this is a new direction that no one had looked into before. And we now have these series of 3 papers, and I've listed all my co-authors from these 3 papers in alphabetical order here. So first, let me give some context on post-quantum cryptography by starting with pre-quantum cryptography. So the cryptography that is deployed today for public key crypto systems is based on algebraic and number theoretic problems. For example, RSA is based on the hardness of factoring. Diffie-Hellman is based on the hardness of the discrete logarithm problem. in the multiplicative group of a finite field with p elements, or the finite field with some prime power number of elements. The elliptic curve cryptography is based on the hardness of discrete logarithm problem in the group of points on an elliptic curve over a finite field. So those are the main public key systems that are deployed today that are used to protect basically our worldwide e-commerce, including really foundational building blocks, which are key exchange mechanisms, encryption, and digital signatures to ensure authenticity. So I usually like to talk a lot about the applications of cryptography, but in the interest of time, I'm not going to include that in this talk. Instead, this talk will focus on algebraic systems, actually for post-quantum cryptography, which means systems that don't have polynomial time quantum algorithms to attack them. And I'll focus a little bit on AI and machine learning and how we can use it in trying to understand the security of these systems. So the race for post-quantum cryptography is really inspired by the major investment that we've seen in the last decade or so in trying to build full-scale quantum computers. Once we have quantum computers at scale that can handle, thousands of qubits, that can do computations faithfully, things that are not possible today, but once we do have those, then we already have actually compilers built that could be used to break existing RSA and ECC systems in polynomial time. So it really is a real concern that once quantum computers exist, if we do manage to build them at scale and being able to do a computation faithfully without losing, too much precision and accuracy, we really will need to replace our existing public key crypto systems that ensure our security on the internet. However, we know from experience, I know from many years of experience of being at Microsoft, and it's very well known in the industry, that it takes years and years and a lot of effort to roll out new crypto systems. So to find and yank out all the existing implementations and to replace them with new robustly engineered systems. ECC and RSA had decades to iron out all the bugs in the security bugs in the deployment of these systems, and there will surely be an analogous process when we're rolling out post-quantum crypto as well. So the NIST, the National Institute of Standards and Technology in the US, has run a number of international competitions. Even just during my 25-year career, I've been involved in and seen them run more than 5 major crypto competitions. And most recently, they ran the post-quantum crypto PQC competition from 2017 to 2022, and ended by standardizing several candidates for post-quantum crypto. And actually, 2 of the candidates that they standardized, including Crystal Kyber for key exchange, are based on lattice-based cryptography. And lattice-based cryptography as a kind of a general field actually already goes back to, in some sense, goes back to the 1980s when the shortest vector problem was already being studied. So the best known algorithms for solving the shortest vector problem in a lattice run in exponential time, and they are basically variants of Conan's algorithm already from the 1980s. But various crypto systems based on lattices were proposed concretely in the mid-90s, including NTRU by Hofstein, Pfeiffer, and Silverman, which ended up they started a company, NTRU, and NTRU was acquired and still exists today. So what is lattice-based cryptography? So first of all, what is a lattice? You can just think of a lattice as a discrete linear subspace of Euclidean space in n dimensions. So in an n-dimensional lattice, you can think of it as just being generated by n linearly independent vectors. And you would just take, I have a silly little picture up here in the right-hand corner, which is just in 2 dimensions, but you would just take all the linear combinations of these vectors, and these points that are in the lattice can also be represented as the vectors from the origin. And so if you connected all these up, you would see a kind of skewed grid that kind of looks like a lattice. So thus the name. So what is the hard problem then that is used in cryptography? Well, the hard problem that we use in most of the existing schemes today, including homomorphic encryption, is a problem called the learning with errors problem. So it actually relies on the hardness of these other problems. There are reductions to the shortest vector problem, things like that. But the way the learning with errors problem is stated is as follows. So if you have a secret vector S, so n coordinates, and then you generate a random vector A, and you take the inner product of these two, and then add some error each time, which is sampled independently each time from a small, like a narrow Gaussian. So it's called an error because it's kind of small, or it's sometimes called noise, also because it's intended to be small compared to Q. And then you take this mod Q and you get the output A. So it's basically a noisy inner product with a secret. And you're given the random vector A, and you're given this noisy inner product B with this secret. So given many of these pairs with the same secret, the first question is whether you can even tell whether these pairs were just generated randomly, mod Q, or whether they're actually an LWE pair. And then the second problem, that's called the decision LWE problem. And then the search LWE problem is, given many of these pairs, can you actually find the secret S? So the high level idea of how this, and that's called learning with errors, meaning can you learn given a bunch of like error prone inner products? Can you learn the secret? So the encryption kind of works as follows. At a high level, let me tell you the idea behind encryption. So encryption adds noise to this secret inner product, it adds this noisy secret inner product to a message in order to kind of blind it. So this is a typical strategy in cryptography, including, like the idea of like a one-time pad, where you had take some message and you want to encrypt it, you want to essentially blind it with something that looks random. But in our case, for example, in homomorphic encryption, we want to have encryption which actually has a homomorphic property and structure, and so that you want some kind of method to your madness, method to your randomness that you are going to add to this message. You're going to blind the message with something which has a little bit more structure. And that allows us, for example, in homomorphic encryption to be able to add and multiply ciphertexts, which is the whole goal of homomorphic encryption. So sorry for a little diversion. Homomorphic encryption is one of my favorite topics, so hard for me to resist digressing into that. But just in general, in encryption, the noisy secret inner product will be used to kind of blind messages. And if you have the secret, if you know the secret, decryption just works by subtracting the secret inner product. So you're given the randomness, and you would just subtract the, the secret, you would subtract the secret inner product. And what you get is basically a noisy version of your message. It's the message with some noise added. And so literally we decrypt by actually rounding. And as long as the error is small enough, you will round correctly and you will get the message. So that's how encryption decryption works with LWE. And then the hard problem here is to kind of decode noisy vectors. So as you can see, if you think of like a lattice that's generated in terms of some generators related to this secret vector, you can actually encode the problem of finding the secret as an instance of finding a unique shortest vector in a particular lattice. So this is called the USVP attack, the unique shortest vector problem attack. And so if you can find the shortest vector in given lattice, then you would be able to break the crypto system. You'd be able to find the secret. But as I mentioned earlier, the best known algorithms for actually finding the unique shortest vector in general are exponential in the dimension. And so that's where kind of the security of these systems relies upon that. Now, I'm not mentioning, maybe I'll mention a few other attacks, but not getting into detail on the other kind of what are called lattice reduction-based attacks. So the basic idea, yes?
There's just one question on the chat. The question is, what are assumptions on Q? I think it's from a couple of slides early.
Great. That's a great question. You're going to see in a couple of slides some concrete parameters. And let me address that. Thanks for bringing up that question. Let me address the question of the size of Q in just a minute. So let's just go over to make sure everybody's on the same page with the lattice problem. And here again, I'm sorry, it's very lame. I'm showing a lattice in 2 dimensions, which is definitely not a hard cryptographic problem. So the idea is that if you have a lattice generated by these 2 vectors, B1 and B2, you can see they're very short. They're essentially as short as possible if that's if the starting point is the origin. And then you can also see that they're rather orthogonal to each other. So that's a kind of a good basis for a lattice. And a bad basis is something which is much longer vectors and much more skew. So you can think of the endpoints of the lattice as being, halfway around the world. But if you're only in 2 dimensions, it's still not going to be a hard problem. So the basic intuition that I like to try to share with everyone about lattice problems and why the dimension matters so much is that in 2 dimensions, this is actually a very easy problem to find short vectors or find the shortest vector. Because what you can do is you can just use kind of the Gram-Schmidt orthogonalization process. So you can just basically project one vector onto the other one and then subtract and then project back the other way and keep going. And you'll very quickly end up with the shortest vector. Now, in higher dimensions, so the idea of the LLL algorithm, which again is from the 1980s, is that you can do this pairwise with many different vectors in the basis. So pairwise doing this kind of project and subtracting type of operation. But the LLL algorithm, it runs in polynomial time, but it finds you an exponentially bad approximation to the shortest vector. So let me kind of answer, I'm going to jump to the bottom of this slide to answer the question about Q. So the fact is that in order to break these crypto systems, what you need is a short vector. For the USVP attack, like I said, you need the unique shortest vector in a certain lattice. But in general, for like the decoding attack, you just need a short enough vector. So what do we mean by short enough? Well, it's short enough compared to Q. So if Q gets too large, and your algorithms are essentially like the same algorithms they would be in characteristic 0. So you're applying these kind of lattice reduction algorithms. And if Q is too large, it's much easier to find a vector which is short enough compared to Q. So what happens then is that like a polynomial time algorithm like LLL will indeed find you a lattice vector which will break your crypto system. So I like to put this in red down here, examples where the LWE problem is not hard is if Q is too large with respect to a certain n. And so that's why long ago, I was actually invited to Virginia. MITRE hosted me to talk to the CIA and the actual Joint Chiefs of Intelligence community on homomorphic encryption. And I think they were a little bit surprised to learn that, you know, the security of homomorphic encryption and these lattice-based systems, it really is a game of setting these parameters correctly. And you can think of it in analogy to like RSA, right? If you were to generate, you know, RSA where your numbers were smooth, then, you know, your factorization problem would be really easy. And even if you have like two equal size primes, if your primes have bad properties, such as like P-1 is smooth or things like that, it won't be secure. So we have a kind of an analogous situation here with lattice crypto. We have to choose the parameters correctly in order for it to be a hard problem. So the hardness of LWE depends on selection of parameters. And so I want to give you some concrete examples. So if you look at the Crystal Kyber key exchange or key encapsulation method, it's called, that NIST has standardized, you'll see that will take, for some versions, they'll take n equals 256, but they have a rank 2 module over a ring that has dimension 256. So it ends up being like a 512 dimensional problem. They also have a 768 version of that. For example, for homomorphic encryption, we almost always start, even for basic types of computation, with the dimension 1024. And you'll notice that all of the ring dimensions that we use are all powers of 2. And that's because in the ring version of this problem, which I haven't talked about, ring LWE, we have special attacks that were found actually in our Win3 paper published in Crypto 2015, which I co-led with Kate Stang. So Q is going to be the modulus, N is the dimension, E is the error vector, which is sampled from a Gaussian with a small standard deviation. So the standard deviation is sigma, but for homomorphic encryption, the sigma is rather small, like around 3. That makes it efficient because you need to control how much the error grows as you do compute in order to still correctly decrypt. And that's very important. So it's sensitive to the size of the error that you start out with. And then the secret vector is going to be sampled from some secret distribution. So the secret has n coordinates, if n is the dimension, and these coordinates could either be sampled from like binary, meaning each coordinate is 0, 1, ternary, where they're 0, 1, or -1, or a Gaussian distribution, which is like the same as the error distribution, or even a binomial distribution, which is kind of like the Gaussian distribution, and that's the one that Crystal Kyber uses. And so, or the one that's the most secure by far, which is uniformly at random. So if you select your secret uniformly at random, that means each coefficient is random mod Q. And so if you're talking about a secret, which is like binary or ternary, it makes sense to talk about like the Hamming weight in the binary case, or in general, kind of like the weight of the secret, which is like the number of non-zero entries in the secret in the binary or ternary, or even the Gaussian case. The reason that I mention Hamming weight is that in applications, sparse binary secrets are favored for efficiency reasons. So you can probably guess that those are going to be the weakest systems, and that is indeed what we find both with classical lattice attacks and with our new machine learning approach. So one more parameter to keep track of is the number of samples that an attacker has access to, and how many samples do you need for your attack to work. So like I said, here's some examples of LWE in practice. It's the NIST 2022 PQC standard, Kyber 512 and 768, has N equals 256, and you can see log Q is rather small. It is around 3,300 or 30, it's 3,300 something. I forgot what the exact prime is. And so the log of that prime is roughly 12. And the secret distribution is actually a binomial secret distribution. So all the coefficients of the vector, the secret vector S, are drawn from -2 up to 2, but in a kind of a stacked binomial percentage. And so the number of zeros in the secret would be roughly 37%. So it's not exactly sparse, but it does have like more than a third of its entries are 0. Homomorphic encryption, on the other hand, uses larger dimension and thus also it can afford to have larger Q without becoming insecure with regard to lattice reduction algorithms. And also uses the standard for homomorphic encryption, which I worked on for a number of years. We created a homomorphicencryption.org standardization community starting in 2017, and we published our standard in 2018, which you can still refer to if you're interested in deploying homomorphic encryption. And in that standard, you'll find that binary, ternary, Gaussian, and random secret distributions are standardized, all with a small error. So sigma, the size, the width of the Gaussian is around 3. And these small secret distributions are standardized, but sparse secrets are not standardized. So there are homomorphic encryption applications where they push for using sparse secrets, but as you'll see from my talk today, it's not a good idea from the security point of view. So classical attacks, I've already mentioned a couple. As I said, going back to the 1980s, the polynomial time LLL algorithm, which is a lattice reduction attack, which is particularly simple to explain, this kind of pairwise Gram-Schmidt orthogonalization. BKZ is a generalization of LLL, which works by projecting lattices onto subspaces of higher dimension. The FPLL implementation of LLL and BKZ is one of the standard implementations, which is used actually by the in the lattice LWE lattice estimator software to estimate the security of different parameter choices. And most recently, the BKZ 2.0 algorithm incorporates a lot of different optimizations into BKZ. And so BKZ 2.0 is the kind of roughly the state of the art for lattice reduction attacks. And as I mentioned earlier, the USVP attack is a concrete secret can be used for concrete secret recovery of LWE. But we also have a decoding and a dual attack in both cases, like in the dual attack, which I haven't really mentioned yet. It requires you to find a short vector in the dual lattice. So most of these systems that we deploy today, given us a certain parameter set, we will decide like basically how fast we think the best attacks run by using, for example, the LWE estimator, or just by estimating the classical lattice reduction attacks. What block size would we need in order for the algorithm to find a vector which is short enough for the attack to succeed? And then given that we think that's the block size, or the block size we would need to get that short vector, what is our cost estimate for running these algorithms with that block size? So that's how the actual security parameters are set today. So I'd just like to pause to see if there's any other questions, because I'm not monitoring the chat before I go to the next part of my talk.
So you want LWE to be hard?
I'm sorry?
You want LWE to be hard?
That's right. You want it to be hard to find. So in the very beginning, when I talked about the LWE problem, when you're given a bunch of pairs, A, comma, B, A is a random vector, B is a noisy inner product, or it's random. You want it to be hard to find the secret. And that's because, like when I explained how it's used in encryption, if you know the secret, the way that the LWE is used is that the secret inner product is used to blind messages. And if you're able to figure out what the secret is, then you'll be able to decrypt the messages. So you want it to be hard.
Thank you.
Mm-hmm. Other questions?
No questions in the chat. Now there's one. Renata's asking, maybe a basic question, but is this error value a continuous one?
That's a good question. It actually is subtle. So as you can imagine, when we're implementing these things, especially mod Q, we need to discretize the distribution. And so there is a little bit of subtlety on the difference between the continuous and the discretized version of the distributions. But there are like theoretical, lemmas that are used to argue that it's justified to use this discretized version of the distribution. Okay, so I'm going to go on to the kind of the next part of my talk. So long ago, long before I actually went to Facebook and Meta, when I was working on lattice-based crypto and homomorphic encryption and applications to private AI and all of that, I thought it was very interesting that we have actually in the machine learning community the assumption that learning with errors is possible. So the learning with errors problem was introduced by Raghib in the crypto community around 2005. And so it'd been around for a while. And so the idea is you're given a bunch of noisy data. So the random data A and then the noisy inner product B. And the assumption is that it's hard to learn from that noisy data, to learn what is S. Whereas in the machine learning community, we actually assume the opposite, is say, well, if you're given a bunch of noisy data, I can use that to find the pattern, and then I can use that pattern to make predictions for future data that comes in. And that's the basis of AI, of machine learning. And so I always thought this was very ironic that these two communities, the crypto community and the machine learning community, basically make the opposite assumption about this particular problem. And so finally, when I went to Facebook, I was able to get the time and the expertise and the compute resources to actually start working on this problem with my colleagues. And so we really wanted to see if we could use machine learning to come up with essentially a different attack paradigm that has never been considered for lattice crypto. So lattice crypto, like I said, it's been around for almost 40 years, and this is just a completely different way of looking at the hardness. So I thought for a mathematical audience that it would be nice to at least just talk briefly about what we mean by machine learning. One of the things that's a problem, like for anybody who lived through the Bitcoin blockchain days in crypto, they know what kind of how annoying it can be to have all the hype. So for many years, we were basically talking about the B word, which could have been either blockchain or Bitcoin, but now they've even taken over our cryptography instead of being the field of cryptography. Crypto, when you say crypto, people think you mean like cryptocurrency. So honestly, it can be kind of annoying to be a scientist in an area which goes through one of these periods of hype. And that's exactly what's happening today with AI. And people are not really understanding the mathematics underlying the systems. And so that's what leads to a lot of misunderstandings and a lot of fear mongering. And so I like to talk about the mathematics basically in the simplest possible term. So I take like the simplest case, which is supervised learning. So supervised learning means that you have some labeled training data. So you have some data, but it has labels on it. So let's say you have a classification task. I'm going to show you a classification task from medicine, which is like measurements of a tumor, and then it's either a benign or a malignant tumor. So the green ones are benign, the red ones are malignant. And so the idea is you have some kind of classification task. You're trying to decide, given a bunch of data, like a vector of data for a patient, is this a benign tumor or a malignant tumor? Mm-hmm. And so the way that machine learning works is that you actually have to derive a function, which is really your model, your machine learning model. You derive it from labeled training data. And then you use the learned function or model to make predictions on new data. So that's the basic idea behind machine learning or AI. And you got to think about also the fact that in order to use this, whatever problem you're working on, the data has to be encoded, like the real world information has to be converted into vectors that are then processed by these mathematical algorithms that we set up. So for example, like for targeted advertising, like your personal profiles are often like, 200 characteristics and they have to be encoded as a vector, or, your history of your music preferences or your credit card purchases, or even health data or like genomic data. So it has to be encoded as a vector in some way. So that's a separate and sometimes ignored portion of the whole workflow, which is taking real problems, real situations, and encoding the data in the best possible way to enable learning. And it's often a very, very important step. It was for sure for homomorphic encryption, for the work that we did on homomorphic encryption for many years. But in general, it's very important for machine learning as well. So here you have some examples. Each row here would be a different patient, and these would be the measurements of their tumor. I believe this was like a liver tumor example. Mm-hmm. And so the idea is that supervised learning would be given a lot of this kind of labeled data, and then you would try to develop some kind of function or model that could then be used the next time a patient comes in. You measure all these same things, and then you try to say, oh, what do we think it is? Is it more likely to be malignant or more likely to be benign? And as you can kind of see, even from the way I'm describing, it's not 100% science. It's an approximate science. So it's never going to be like 100% accurate. So the way that the way that machine learning model training works is very complicated. And I'm only picking a really, really, really basic small example just to give the idea. So the most basic possible algorithm you can think of basically is the linear means classifier. So imagine dividing your training data into two classes according to their label. So I can't draw it for you. Again, I can only draw it in 2 dimensions here on these slides, but that data was like, there were, I don't know, about 15 columns here, 15 to 20 dimensional data. And so what you would do is you would cluster all the data that's labeled green for benign, cluster all the data that's labeled red for malignant, and you would compute the mean vector for each of these classes, and then you would compute the difference between the mean and find the midpoint, and define a hyperplane between the means, which separates the two classes. So that hyperplane would really be your model. It's the function that you computed that divides your two classes. And so then when you get a new data point coming in, you would just decide, well, which side of the hyperplane was it on? Which class do I think is more likely? Okay, so like I said, this is a very, very basic example. And here, this picture isn't even very good. The blue dots are supposed to be red. And there's a number of different problems and issues that the scientists in machine learning have been addressing for decades to come up with, better, more complicated models and deal with all kinds of weird distributions and all kinds of problems that can come up. But I just wanted to kind of give you this example of how underlying a given problem, you may be able to talk essentially about the geometry of the problem in this sense. So the strategy in general for the supervised learning is to compute a model which is a decision boundary like the hyperplane. So the hyperplane is now an example of what I'm calling a decision boundary. That's your model. And that decision boundary will generally be computed by defining some kind of a loss function. And this could be like the least squares distance from all the points to whatever your decision boundary is. And then as you add more and more points, you update your decision boundary to try to minimize this, this loss function. And then we have very standard methods such as stochastic gradient descent, which is basically multivariable calculus that allows you to minimize this loss function. And this kind of thing is done, for example, in logistic regression or linear or logistic regression, and then led to eventually the development of the field of neural nets or deep neural nets, which is many iterations of this kind of logistic regression layers. So you have these deep neural nets and eventually a particular form of the architecture, which is called transformers, which is what I'm going to talk about today. So our goal when I started at Facebook, I hired two interns, Emily Wenger and Mingji Chen, and worked with a research engineer from our Paris lab, Francois Charton. And so we set out to attack the learning with error problem by using machine learning. So as a reminder, remember you're given these samples A comma B, and you want to find S, where S is the secret vector. So the key intuitions, remember the learning with errors problem assumes it's hard to learn from noisy data, but machine learning models are actually good at learning from noisy data. Learning with errors problem is actually a lot like linear regression, except for it's mod Q. Remember, we're always taking our elements mod Q, and that kind of messes things up for the machine learning models. And in fact, machine learning models so far, we've been working on it, but are not very good at modular arithmetic. And in fact, my Win6 project was just in March, is just focused on training machine learning models for doing modular arithmetic better. And it's a hard problem. So let me tell you what we've been able to do, even though modular arithmetic is hard for machine learning models. So we in our first paper with Wenger and Chen and Charton, we assumed that the secret is binary, so just zeros and ones, and that it's sparse, so that means not very many ones. And we were able to train models which, given a random vector A, will predict B. So the model has been trained on a whole bunch of samples, A comma B, for the same secret. And now, which is exactly what you're given in the learning with errors problem. And now what the model does, its capability is given A, it will predict B. And of course, it doesn't predict B very accurately. But what we found is that even if it even starts to learn to predict B, so something like, between 20 and 30% accuracy is plenty of accuracy in order for us to use it as a distinguisher, a cryptographic distinguisher, to use as an oracle to let us find the secret. So all we need is for the model to start to learn to do this task. Well, it doesn't have to be like 95% accurate, which is like what you usually want from your machine learning models. So we're able to recover sparse binary secrets for small size LWE problems. SALSA refers to secret recovery attacks on LWE via sequence-to-sequence models. So sequence-to-sequence refers to the transformer models. So we had these three elements of the SALSA ingredients. The recipe is the transformer model, which we need to train. And that doesn't take that much time, but you have to factor in that we have very highly optimized versions of these machine learning models that run on GPUs, because in the industry, in the whole, arms race that we're in these days with the large language models. So Llama is the meta open source large language model. ChatGPT is the proprietary OpenAI model. In these kinds of applications, the machine learning steps are the main cost, and it's very, very costly to train these large models. And so they've been highly optimized to run on GPUs. And so we can train our transformer model very, very quickly using this infrastructure. And our models are very small. They're tiny compared to large language models. So we're not taking advantage of the full force of the current industry. And even given the the transformer model, then we have to actually run our secret recovery steps to figure out, to guess and check the secret. So secret recovery and secret verification are the second and third steps of our algorithm. So the performance that we got with SALSA is kind of demonstrated here. That we don't need to go into details of these graphs. It's just trying to show you that even if the test loss just starts to drop, then we start to recover secrets immediately. And SALSA only worked on small, what I would call toy problems, up to dimension 128. And sparse binary secrets with Hamming weight 3, and in smaller dimensions 4 or 5, but very small Hamming weight secrets. So it was really kind of a proof of concept, but it allowed us to develop these different secret distinguishers. And so let me just give you the basic idea of how the distinguishers work. And we've actually now generalized these. But the basic idea is that if you have, imagine you have a binary secret. So you have zeros and ones in your secret, but when you take the inner product with a random vector mod q, what you're really doing is just doing a subset sum. You're just picking out some coefficients out of that vector A, and you're adding them up together. And so when you're predicting B, if B in mod q, by the way, and up to a small error. So if you're adding a small value like 0, 1, 2, 3, something like from the Gaussian error distribution, you're still staying in the same region. You're really, when you're asking the transformer model to learn to predict B, you're asking it to learn to do this subset sum. So it gets to see a bunch of subset sums from a bunch of random vectors, and now it needs to predict whether, like for a new vector, what should be the subset sum, approximately, and mod q, by the way. So if we take our vector, if we look at our secret S, and if Si is a bit of in the secret, if it's a 0, then it's not contributing to the subset sum. So when you take a random vector A, and then you add some large value, let's say, to the ith coefficient of A, and then you give that to the transformer model. So give A to the transformer model, and then give what we're calling A, bold A sub C to the transformer model. You expect it to give, if it's learned anything, you expect it to give you a relatively similar output. But if Si was actually a 1, then adding a large value C would drastically change this subset sum. So this is the high level of our distinguisher, what we call our secret distinguisher. And of all of our methods that we've tried, and even a combination of the methods, the distinguisher method is the one that's scaling the best to large dimensions. So we also have some other methods, this direct secret recovery and cross-attention method from our PICANTE paper, but the distinguisher, this one that I just described, is the main one that we're using as we scale up. So I think I'm looking at the time. Do I just have a few more minutes left, Leah, and then I should leave some time for questions?
Yes, please. Yeah.
Yeah, okay. So I just want to kind of highlight the differences between SALSA, which was at NeurIPS last year, and our new papers, PICANTE and VERDE, which are appearing this December. So SALSA, we actually needed access to 4 million LWE samples, which is a lot. That's like thinking of somebody having used their secret, to encrypt something like 4 million times. And we also were only attacking small dimension and small Hamming weight and only binary secrets. Whereas in our new work, one thing we've been able to do is show that we can actually subsample from the 4 million samples. I'm sorry, we can generate only 4n samples and subsample from those to generate data, a data set of size 4 million. So we only need 4n, like a linear number of LWE samples, which is good for our attack to work. We're able to do much higher dimensions, like 350 and 512, and much higher Hamming weights. So like these problems are what we call medium to hard problems. They're very hard in the sense they cannot be solved with exhaustive search and in our lifetimes. And they also compare favorably with lattice reduction algorithms, which I'll explain a little bit more in a minute. So high Hamming weight, high dimension, and more general secret types. So we're able to attack binary, ternary, and Gaussian sparse secrets. So that's kind of a high level summary of where the project stands. And I'm skipping over a lot of the details of these generalizations and how they work, but I just wanted to share this kind of comparison with classical attacks, with the USVP attack in general. And one of the problems that we're facing in lattice-based cryptography is that although in many applications, including the NIST standard, we use special assumptions like secrets from very small distributions, such as binary or binomial secrets. And we use assumptions like small error or sparse secrets. All of these are very, very special assumptions, which are not captured by the Darmstadt lattice challenges, which have been around for quite a while. And you've got a lot of people working on Darmstadt lattice challenges, but you don't have a lot of people working on attacking these LWE instances with these special assumptions. And so in order for us to compare with the state of the art, we actually have to implement a lot of the state of the art classical lattice reduction attacks ourselves. And we're not the experts on that, and we didn't have that much time for doing that. So these implementations of the USVP attack are just our own implementations, but just provided here to kind of give you an idea. So if you go down, and the person who was asking about the size of log Q earlier, so this is a small dimension n equals 256 with binary secrets, because that was the largest way that we could get to our USVP attacks to run. In the higher dimensions, they wouldn't even run. But running them in dimension 256, we're able to get this comparison where, as we noted, the smaller the Q, the harder the problem. So if you look at the bottom row here, when log Q is 20, that's an easier problem. So we're able to attack like Hamming weight 25. We do pre-processing of our data on literally thousands of machines, but in 7.5 hours. And that's an advantage of our method because that step is parallelizable. And then our training succeeds in about 5 epochs, which is a total of, with both stages combined, about 15 hours. Whereas the lattice attacks in these same ranges are roughly in the hundreds of hours, and it ranges quite a lot, which is a little bit alarming. But some instances never terminate, some terminate in like 400 hours, some in 500, and some in significantly less, like 135, 167, and 76. So anyway, in case, like just even in this small dimension, you can see already a big improvement, including when you go down to log Q equals 12. So this top row here, which is the size of log Q used for the crystal Kyber, we can attack it like in 4.5 hours total, and the USVP attacks that we ran just never succeeded. So that just gives you kind of a data point on the comparison. And the main things that we want to do going forward is we want to improve the model's ability to learn modular arithmetic. That'll allow us to expand to different types of secrets. We want to decrease the pre-processing time and our compute requirements, which involves considering other options for how we pre-process the data. So I'm sorry I had to skip over some of the details of those things, but I thought it was more interesting to try to explain that kind of the general landscape of post-quantum crypto and lattice-based crypto, along with machine learning and how machine learning is relevant in this new world of, instead of post-quantum crypto, we should say post-ML crypto. So thank you so much for listening.
Thank you so much, Kristen. Yeah, I guess we'll take some questions. There was a question towards the end of your talk by Hamid Yousefi. So Hamid was asking, I think it was a few slides earlier, how many instances do you use? And what's the metric and how good are the predictions?
Okay, good. So let me, oh, why isn't this going back? With my, for some reason or other, I needed access to my camera. So let's go back to.
I think it was around this slide and then the one before it. That's
Yeah,
one.
so here, we could actually get away with a little bit less than this in more recent work, but here what we're using is 4N samples. So like if N was 256, then we're using, around 1,000 samples. So that was the first part of the question. How many samples? And then what was the next part of the question?
What's the metric and how good are the predictions?
How good are the predictions? I think there must be referring to the accuracy of the machine learning model predictions. Is that what they mean?
Hamid,
Hamid, do you want to specify? Because the model predictions don't have to be very accurate. They, like I said, can only be like even 25, anything, honestly, but 25%. Just the less accurate they are, the longer we have to run the transformer. But even like 25% accurate would be enough to actually fully recover the secret. So the process, the way it works is that we would, so here you have some graphs. This was from SALSA and not from PICANTE or VERDE, but you would see like the test loss starting to drop. And as the test loss drops, the accuracy of the predictions is going up. Now, again, we're not actually using this information in our attack. We are simply running the attack, which is outputting B, and then we're using our distinguisher method for generating a secret SI. So we'll set the secret. I'm sorry if I didn't explain this well enough, but we'll set the secret bit equal to 0 if these values are pretty close to each other and we have some threshold, and if they're pretty far apart from each other, then we'll set it equal to 1. So that's a linear thing. We go through all n bits, and then at the end we test whether that secret is most likely the correct secret by testing it on a bunch of more samples, A comma B samples. And if it is the correct secret, then our B minus A dot S will be very, very close to 0. It will approximate the error distribution. If our S was wrong, then B minus A dot S will look random. And so then we can see, we didn't find the secret, we better keep going. So I think the fact that maybe I didn't explain that clearly enough, I hope this helps to answer the question.
Thank you, Kristen. There are still a couple of questions on the chat, and I know Stanley Shao has his hand raised as well. There's a question from Kate, but it's pretty long. I don't know if you have access to the chat, or do you want me to read it for you?
Okay, wait, let me see. Okay, there's a question that's asking about whether there would be a metric of similarity between different secrets, because indeed it's quite a strong assumption to assume that you would even eavesdrop a linear number of secrets, linear in the dimension, even though in crypto that's a very standard assumption that you would have access to a linear number of samples. But then this comments from Kate says, my thought is that there may be a metric of similarity. Is there any desire to progress this research to training on highly similar secrets? That's a very interesting idea. My thought is that some people using LWE might reuse a method of generating and constructing secrets, leading them to be more similar. This could perhaps be used to recover the way they create secrets, as opposed to a particular secret, reducing the search space for discovering their secrets. So that's a great idea. And I don't think we've tried that. But something similar that we are trying, and which would fit into this, is we've in our current project, my intern from this summer, Sam Stevens, is working on doing what we call pre-training. So pre-training on a number of secrets, but we weren't assuming that they were similar to the other secret. We're just random secrets. And then using pre-trained models and doing essentially fine-tuning to bring down both the amount of data, like the amount of data pre-processing we have to do on the new secret. So that's a somewhat related idea, but we have not used the idea that you mentioned. So please get in contact with me if you want to follow up on that.
Mm-hmm. The other question from Wayne, based on your work, do you believe that ML is going to make lattice-based cryptography obsolete? And if so, what are better options for post-quantum crypto?
Oh, that's a great question. So I think that our work is going to, or hopefully should, very quickly suggest to NIST that they consider other standardizing just random secrets, because our methods don't work against random secrets yet at all. And random secrets are not that much more costly to deploy, or don't have that many downsides for things like key exchange. And there's just no reason, I don't know why they didn't just pick random secrets to begin with. So I do expect to see that change rather quickly. I think that would make sense. However, so then whether we'll be able to extend these methods to random secrets, I really don't know, because right now our methods are limited by the fact of not being very good at modular arithmetic. Mm-hmm. So if we can get better at modular arithmetic, then training models to do modular arithmetic, then I expect to see significantly more progress, and that could eventually really endanger lattice-based crypto in general, because our methods scale extremely well to high dimensions. They're like essentially like linear in the dimension in our methods so far, given the way that like we have to scale Q with N, so it's a little bit hard to tell, but our methods do not suffer from the dimension going up at all. So they suffer from Q getting smaller because we're so bad at modular arithmetic. But so that's kind of my prediction. The other standards that were really considered in the essentially the fourth round of post-quantum crypto PQC competition were code-based cryptography. But once we can do modular arithmetic, I think we'll be able to develop ML attacks on a lot of different crypto systems. So I'm not holding out hope that code-based crypto would be significantly different than lattice-based crypto from this point of view. And then there's other systems such as like a rainbow, like multivariate cryptography, like solving large systems of nonlinear equations in many variables. And then there's my favorite, which is isogeny-based cryptography, which I introduced with my co-authors, Eyal Goren and Dennis Charles in 2005. And that made it to the fourth round of the post-quantum crypto competition. And the SIKE, the key exchange, was actually broken because it provides a lot more auxiliary information. But the underlying hard problem is still open, which we introduced in 2005, and that is finding paths in large supersingular isogeny graphs. And that problem is the basis for a whole community continuing to investigate the hardness of those problems. And I have no idea how we would use machine learning to attack those. So, so we still have some other options out there, and we'll have to see how it progresses, but it does depend on whether we can make significant more progress to unblock ourselves with the machine learning methods on modular arithmetic.
Thank you, Kristen. Maybe, do we have time for one more question?
Sure.
Okay. Stanley here. Stanley, go ahead.
Hi, thank you very much for that talk. I'm very glad that I was able to listen in, because you explained certain things very clearly about, you know, what is like the nature of AI. So my question is, do we have a good theoretical framework to understand what is and what is not quantum safe? Like in a crypto system, is there some sort of criteria where you can apply that's easy to understand whether it's going to be secure before or after quantum computers get to scale?
No, the short answer is no, we don't. So currently what happens is there's fairly small number of people that are good at coming up with new quantum algorithms for things. So I worked with some of them at Microsoft Research in Christos Forre's group, so Martin Rutler, for example. And so these are people that are really skilled. For example, we had to come up with a new quantum algorithm for modular inversion, like assuming a certain quantum architecture had been realized, like a nearest neighbor architecture or something like that. So people that are good, there are not that many people that are really good at quantum algorithms. And so we have Shor's algorithm, and we have a bunch of applications of Shor's algorithm. And so if you can formulate your problem easily as kind of like basically like a subgroup problem in an abelian group, then you'll basically know that Shor's algorithm is going to work, or you kind of get into the details and make sure. And so there's that bit of information. Like if you can encode your problem in as an instance where Shor's algorithm will work, then yes, we can have an answer, yes. But other than that, we do not have an easy way to say whether these new proposals are quantum safe. What we need is people that know how to design quantum algorithms, trying to attack them. So that's my view anyway, at the high level. Maybe I need to think about it a little bit more, but that's my initial answer.
Yeah, so based on my understanding, I mean, this is different from theoretical computer science because you have in theoretical computer science, you just start with a Turing machine, which is an infinitely powerful computer. So there's no distinction between like a conventional or quantum computer from that regard. So a lot of the literature there is useless to answering this question. So it's very hard to come up with like some criterion to decide. Like you try it, and if you find one, then great. But if you don't find one, doesn't mean it doesn't exist, right?
That's right. I'm going to refrain from commenting anymore on quantum algorithms because it's not my main expertise. But so thank you so much, all of you, for listening and for the opportunity to talk about this work.
Thank you. Thank you so much, Kristen, for a great, amazing talk. Please join me in thanking Kristen again.